Okay, so multiple representations of a coordinate point in polar. It says give 3 different representations of the coordinate point to 30 degrees. So, okay, I guess I have mine drawn already, but let's recreate something right quick, okay? So draw an X and a Y. Let's go out just 2, maybe 3, so we can do another one. Those are not the same. Those are now not the same. Okay, and let's create our circles, our radii. If we'd been in school, then I would have had some graphs printed for you, but, well. Okay, now let's do the angles. So, halfway. Halfway. Man, that is really lopsided. Oh well. Okay, so we got our basic circle. Now what I want us to do is write down the coordinate point 230, and let's plot that. So here's 30 degrees, and here is out 2, a radius of 2. So that is the coordinate point 230 degrees. Now what I want to do is talk about different representations of the same coordinate point. On the x and y Cartesian plane, there is one representation. You go x and you go y. You know, it could be left, it could be right, but there's only one way to describe each coordinate point. There are multiple ways here because angles don't have to be approached just one direction. Nor do you have to have the same radius. Well, the directed value you do, but you can have negative radiuses, right? Okay, so this coordinate point right here, 230 degrees, is going at it like this from that direction. We know that we can also go backwards the same, well, not the same, but we can go backwards the coterminal degrees, and it puts me in the exact same spot. So I could say, instead of 230, I could say 2 negative 330. So remember, coterminal angles are angles that start in the same spot and end in the same spot but go in opposite directions. Okay, those are 2 different ways to get to the same point going with a positive radius. But then you also have the option of a negative radius, right? So what I'm going to do is I'm going to put an X right here. Okay, this is directly across the pole from this coordinate point right there. So if I can get to this spot forwards and backwards, then I can also get there as long as my radius is negative. So what I could say is, well, I know this is 210 degrees, right? So if I go forward 210 degrees, but then I have a negative radius, then it'll pop me across the pole and put me back in the same spot. And then lastly, I could go to that spot right there backwards, negative 150 degrees. This is 150, so backwards, so 150 would be right there, and then with a negative radius. Okay? And you can see that these two angles, 30 and negative 330, 210 and 150, in the absolute value they add up to 360, these two and these two. Because these two are coterminal and these two are coterminal. So your angles, when you have a positive radius, the two angles should be coterminal. When you have a negative, the two angles should be coterminal. Okay, so that I gave you 3 more representations of how to get to the coordinate point 230 degrees. Now let's do this one. And we're going to keep it in radians, okay? So we've got the coordinate point, which we're going to change. We're going to change that to 1, 3 pi over 4. Oh, wow. I'm not going to draw more rings. Okay, so just a reminder, this is 1/4, this is 2/4, this is 3/4 right here. So 3/4 pi. Um, if I'm trying to get to 3/4 pi, or 1 3/4 pi, then I go out 3/4 pi, and then I go a radius of 1. So that is right there. Okay, so if I go forwards, then that is just right there. That's the initial coordinate point. If I want to get there going backwards, then I just need to go from, let's see, here to there. And there's two different ways to do that as far as figuring out the angle in radians. You could, well, actually three. You could take the degrees and convert it to radians, right? You could add or subtract 2 pi. So if you go backwards 2 pi from here, that puts you in the negative. Or you can think, okay, well, this right here is 3 pi over 4. If I go backwards, like what is this equivalent of going backwards? It's a full pi plus another quarter of a pi, right? So if I go a full pi plus another quarter of a pi, I know that that right there is 5 pi over 4. Yeah? So going to here is to go backwards 5 pi over 4. Another option is just say, like I said, 3 pi over 4 minus 2 pi. So subtract a full rotation. And what I get is times by 4 times by 4, so that's 8 pi over 4, and that would be negative 5 pi over 4. You can also just take 2 pi and subtract 3 pi over 4 and say, well, what's left over? And you would still get 5 pi over 4. So either way, whatever speaks to you, that's, whatever you need to do to figure out what that is. So we could say, if I go still a radius of 1 and backwards 5 pi over 4, then I'll get to the exact same spot. Okay, but I could also head to the opposite, or across the pole. So here, right here, here's it here, right here. I could head to this spot right here, and then if I have a negative radius, it would pop me back over there. So if I say, let me go forwards first. If I go forwards, it's like, how many radians is that? That right there is 7 pi over 4. And then I would have to have a negative radius. And so if I go positive 7/4 pi, and then have a negative radius, that would pop me from here across the pole to there, and I'm in the exact same spot. And then the last option is I can go backwards this many radians, which we know is just a quarter pi. So if I go backwards a quarter pi, and then with a negative radius. So go backwards and then pop over. Okay, I hope that makes sense. All right. I think we're good on this. If you would like to try this right quick, if you want to just use your other graphs to plot it if you need it, I'm going to just write them right quick, and if you want to check your answers, feel free. If you want to skip through this, feel free. So the original coordinate point is negative 60 degrees 3 with a radius of 3, so I'm going to go backwards 60 degrees and then 1, 2, 3. So that's my original, and I went this direction. So if I go forwards, then one of mine could be 3 and then 300 degrees. And then my other option is to go here. So I could go and then pop across the pole. So I could say positive 120 degrees, but have a negative radius. Or go backwards 240 degrees. And the only reason I'm pointing at this is because I know that these two, like, if I go backwards 120, it's right here. If I go backwards 240, it's right there. So they're mirror. They mirror each other right there. And then negative radius. Backwards 240, mirror. Forwards 120, mirror. Okay. Now, here I actually have an image where you can see the polar versus the rectangular coordinate system. Obviously, on the axes, they land on the exact same spots. Those coordinate points are the exact same. But you can tell that in the polar coordinate plane, like this coordinate point, while it's pretty on the polar, is not necessarily pretty on the Cartesian. Because you're talking about radii as opposed to x's and y's, So it's interesting. It's like we're more talking hypotenuses of triangles as opposed to legs. You know what I mean? The left and the right, the base and the height. I said the left and the right. The left, right, up, and down. Okay. So, the thing about it is that we do need to be able to, like, convert from one system to the other. So if I give it to you in Cartesian, can you find it in polar? And if I give it to you in polar, can you find it in Cartesian? So for that reason, let's draw a little x and a y. Right, so any coordinate point can be described in two different ways. It can be described as going out an x and up a y, or it can be described as going out a radius at a certain angle. Right? So take a second and write that down, or draw that image. And then what I want you to do is think about the relationship these variables have. Not all four of them at one time, but some of them, right? So if I forget the theta for a second, I've got a right triangle. I've got a leg and a hypotenuse. Okay? So the Pythagorean theorem says that I know x squared plus y squared equals r squared. Okay? It also tells me that, so that's like the two x's and y's and then one of the polar, right? So it'd be really nice if I could get the two x's and the y's and the theta, because then that means if I know the x and I know the y, I can find the r. I need to know, if I know the x and I know the y, can I find the theta? Yeah? So what relationship do these have? Well, given an angle and a right triangle, this is the opposite and this is the adjacent. So I know that tangent of theta equals y over x. Yeah? Or theta equals tan inverse of y over x. Okay. So if I need to find the r, and I know x and y, I can find it. And if I need to know the theta, and I know y and x, or x and y, then I can find it. Cool. Okay. But then, what if I know the r and the theta, and I need to find x and y? Okay, so what I'm going to do is, again, I can only have two unknowns with one unknown, or two knowns with one unknown. So I'm going to cover up the x for a second. If I want to find y, given r and theta, then I need a relationship between these, right? So what I know is that given an angle, this is the opposite, this is the hypotenuse, so that would mean sine of theta equals y over r. So notice how here, like, r is alone by itself, and I could solve that. R equals plus or minus the square root of x squared plus y squared. True? Okay, so the radius could be the plus or the minus of that length right there. So I got r by itself and I got theta by itself in terms of x and y. Well, I need y by itself in terms of r and theta. If I know the radius and I know the angle, then what's the y value, right? So I just need to multiply by y, or by r, and then I can say y equals, so multiply both sides by r, that y equals r sine of theta. Okay? And then, if I need to know the x, then I use this relationship. I know that cosine of theta equals adjacent over hypotenuse. And I do the same thing, multiply by r. So if I multiply both sides by r, then I get x equals r cosine theta. So we've got four equations relating these variables. If I know, I have polar to rectangular right here. That's the first type we're going to do, but I'm going to go ahead and write them down in the order that I did them. So if I know, and I keep saying Cartesian, Cartesian is also called the rectangular coordinate system. So rectangular slash Cartesian to polar. Okay? So if I know x and y, then I can solve for r using this formula or taking the square root. And then I can solve for theta by taking the tan inverse of the y divided by the x. Okay? Sometimes that would need to be a calculator problem, but a lot of times what we do is we keep it to the angles that we know using the unit circle. And then if I want to go from polar, so knowing r and theta, wow, that was terrible. So if I want to go from x and y to r theta, and then here if I want to go from polar to rectangular, that means go from r theta, wow, to xy. Then I need, I'm going to go ahead and start with the x. X equals r cosine theta, and y equals r sine theta. I cannot draw theta right now. Okay, so I'm going to keep that handy and we'll use it as we go through. Find the rectangular coordinates of each point. So I've got this coordinate point P, and it's a -2 radius and an angle of -5π/6. So what I'm going to do is recognize that I have an r and a theta, and I want x and y. Yeah? So I guess I could say the rectangular coordinate point would be what? Because that's what I need. So using this, I know that if I know r and theta and I want x, then I can use that, right? So x equals r, -2, times the cosine of theta, -5π/6. Okay, so this is where we get back into, as far as the unit circle goes, what those coordinate points are. Let me find that unit circle I drew at the beginning, so we can just draw on that. I know I drew it somewhere. Yep, okay. So let's draw our coordinate points on there. I know that this coordinate point is 1, 0. I go out on the unit circle, right? Unit 1 to the right and up 0. This is the coordinate point 0, 1, -1, 0, and 0, -1. That's on the unit circle and on the xy coordinate plane. This point right here, if I had my unit circle and this is the radius of 1, then if you remember, we developed them using special right triangles, but then we memorized them using a trick. Okay. So they're all they're all fractions cut in half. So I'm just going to draw that real quick so I can use that. If you want to fast forward through this, you can, since you have, or skip, since you have a copy of it maybe with you. Which would have been nice, but I didn't print one off for myself. Okay. Remember, you can use the shortcut 0, 1, 2, although it's square root, and 3. 0, 1, square root, 2, square root 3. And then 0, 1, square root 2, square root 3, 0, 1, square root 2, square root 3. And in this coordinate, x is positive, y is negative, so that would be negative y values. And just as a reminder, like, we figured this out using special right triangles, knowing that in a 30, 60, 90, yeah, whatever the hypotenuse is, the short leg is half that, and the long leg is the square root of 3 times the short leg, so that would be square root of 3 over 2. So this is to the right, square root of 3 over 2, and up 1/2, so to the right, x, and up, y. And then vice versa for this, and then this one, whatever the hypotenuse was, or whatever the legs were. You could say if this was 1, 1, that was square root of 2, but because that was 1, these became 1 over the square root of 2, and that rationalizes the square root of 2 over 2. Okay, we're going to do this, and then we're going to pause or stop the video so we can start a new one, because I don't know if the audio and visual are getting off yet. Okay, I need cosine of -5π/6. So I know 5π/6 is right here. So that's forward 150 degrees. So I'm going to go backwards 150 degrees, 0, 1, which means square root of 3, and they're both negative in this quadrant. So cosine of -5π/6, which is this right here at 7π/6, cosine is negative square root of 3 over 2. So -2 times negative square root of 3 over 2, negative times a negative is positive, 2 simplify out, that is the square root of 3. So we would go to the right, square root of 3, and let's find the y value. So y would be our sine of theta, so our sine of -5π/6, using this again, y equals r sine of theta. And so sine of -5π/6 is the -1/2, so that would be -2 times a -1/2. The 2's would simplify out, the negatives would simplify out, and that would be a 1. So let's see if that makes sense. If I were to go -5π/6, -5π/6 puts me over here, and then the negative 2 pops me across the across the pole, so that would be like, 1 and then 2 and then 1 and then 2, so it would put me right here. So that does make sense as far as going to the right square root of 3 and up 1 if this right here is 2. If I have a right triangle. Let's make sure that that fits the Pythagorean theorem. A squared plus b squared equals c squared. Square root of 3 squared is 3, 1 squared is 1, 2 squared is 4. Cool. Alright? You don't need to check it every time because it should work out, but if you want to check it, that would be a way to know if you're correct. Alright, we'll do one more on this one. The coordinate point 3, 270 degrees. Now this one, I could use this, but I don't need to. I know because 270 is already on the axes, right? So if I think about the coordinate point 3, 270, that's an r and that's a theta. If I were to just sketch that, right? Go 270 degrees, and then outer radius of 30. Right there, right? I already know what coordinate point that is. I know that that is an x of 0 and a y of negative 3. But I can prove it just by using that formula. X equals r cosine theta, so x equals r times the cosine of 270 degrees. Well, the cosine of 270 degrees is 0, right? That's the x. Cosine is the x. It's the adjacent. So that would be 3 times 0, which is 0. Y equals r sine of theta. Okay, so sine of 270 is negative 1. So that would be 3 times negative 1, which is negative 3. And so the rectangular coordinate point is 0, negative 3. If it's on one of the axes, you don't need to use your formula to figure it out. Okay, I'm going to stop this video and pick it up in just a second.